Hello everyone. For the past few lessons, we have been looking at the nature of light and matter, and we are going to continue that train of thought by thinking about light in particular and how its properties influence the motion of objects, how light's properties influence the motion of objects. Now that might sound a little bit unusual, but it is the topic of special relativity, which is what today's lesson is all about. So, special relativity is part of this area of study. Today we're going to be learning about frames of reference. Particularly, by the end of today's lesson, you should be able to define what's called an inertial frame of reference or an inertial reference frame. You should be able to identify them. If you had a couple of different options, you should be able to pick that one's an inertial reference frame, that one's not. And you should be able to calculate some basic relative quantities when it comes to things moving relative to each other. To start, I think it would be really good to actually show you what relativity is and some of the strange observations that we've spotted in nature that can't be explained by regular motion and kinematics and forces that we've learnt in both year 11 and both in year 12 so far. So to start, I'd like to play a short video, just a minute and a half video. Let me switch screens here. And I'm hoping this will play for you. So sit back and please watch.
Physics is all about the motion of things. How planets and stars move, how electrons and protons move, how the movement of molecules results in emergent properties like temperature, and so on. The role of relativity in physics is to study how that motion looks from different perspectives. Here I'm using relativity in a general sense to mean from any different possible perspective, moving, accelerating, or otherwise. Special relativity in particular is concerned with how motion looks just from a limited or special set of perspectives, which we'll get to later. But either way, relativity, special or not, is about how the motions of things look from different perspectives. Like if you were looking at the Earth and the Moon, depending on where you were and how you were moving, it might look like the Moon is moving around the Earth in a giant circle, or back and forth on a straight line, or that the Earth and Moon together are tracing out a spiraling path through space. But if the motion of the Earth and Moon can be described in such different ways, what does any one of these descriptions actually tell us about the Earth and Moon? Is one of them right and the other's wrong? Is there some preferred perspective for observing the Earth and Moon that gets the closest to the true description of what's happening? It's the goal of relativity to answer these kinds of questions. In fact, relativity can essentially be summed up as two basic ideas. One, to figure out how objects and their motion look from different perspectives, and two, to notice which properties of objects and their motion don't look different from different perspectives. We've already given an example of number one, with different...
Okay, I will stop us there, because he does talk about some higher order stuff pretty quickly. But as this video showed, relativity is about understanding motion from different perspectives, seeing what changes and what is the same. So let's dive into that train of thought and see where it leads us. So before we dive into that train of thought, here are some interesting things that we have noticed in nature. And it turns out that this concept of perspectives is actually a way to explain the answer to these problems. I'm not going to explain them all today, but I do want to show you the outstanding questions that we had. So for example, in nature, there is a small particle called a muon, and that decays into an electron in about 26 nanoseconds. However, when a muon travels at close to the speed of light, it actually lives 184 nanoseconds. Its lifetime is extended. Somehow it lives longer just because it's traveling faster. Secondly, when objects move near the speed of light, the perception of distances also changes. Space actually contracts according to them. Moreover, we've developed devices called the atomic clock, which has got to do with these fast-moving electron transitions in particular elements, and it allows us to maintain almost perfect accuracy, as this third statement says, accuracy to 1 second for the next 1.4 million years. Lastly, and this list certainly isn't exhaustive, but if you use the kinetic energy equation 1/2 mv squared for objects moving near the speed of light, you would actually be completely incorrect. So that equation actually no longer applies near the speed of light. Now I'm hoping you would have identified that the fact that we're talking about speeds close to the speed of light, I'm talking about that in every single one of these dot points. I'm talking about very, very fast moving objects. So for everyday circumstances in motion, what I'm about to teach you and what we're about to go through over the next week isn't really relevant. We don't really experience special relativistic effects at all every day because we don't travel at the speed of light. But some things do. And their motion is affected by the properties and the phenomenon that we'll learn about when we go through this unit of special relativity. So to start with this topic, I want to first talk about frames of reference. So there's your subheading. I please invite you to write this into your books. Okay, frames of reference. So to start off, I want to ask a question, and I'm asking it to a blank room, so I'm just hoping you will think as I'm talking about it. But do you ever really notice when you're moving at a constant velocity? So as an example, let's say, oh, is this drawing? Yes, it is. Let's say there's a chair here, and you're sitting on the chair. There's you. For some reason, very, very happy that you are sitting on the chair. And let's say you close your eyes, and you block out your ears. You have no other perception of the world around you, nothing to look relative to or hear things relative to either. Do you know that you're sitting still? Well, you probably would. Just because you know when you're sitting still based on how you feel with respect to the chair. Of course, if the earth was to suddenly shake or your friend was to suddenly nudge you, you would feel your balance change and the forces on your body change, and you know you're probably not staying still anymore. You're moving in some direction. But I invite you to think about this case. What if you were, say, in a train cart? So this is you. You're sitting on a little couch here, and there's a window inside this room, and you're sitting here, and you're looking outside the window to the outside world. Now, let's say I painted this entire window black. Yep, and I gave you earplugs, and you plugged them in. Would you have any idea how fast this train is traveling? Would you? Now, you could be traveling at 0 meters per second. You could be traveling at 100 meters per second. You have no idea. You have nothing to look relative to infer any information about your speed. However, if the train was to speed up or slow down, you might get pushed back into your seat or pulled forward. And so that gives you clues as to how your motion is changing. Right? You can feel acceleration, but you actually don't feel velocity. A really typical example, and this is if you've flown in an airplane before, but when you're in an airplane, you're traveling at, 400 kilometers per hour? But when you're sitting in that seat, assuming you don't have turbulence, you actually don't feel like you're moving. You know you're moving by just logic of, I've taken a flight and they typically go from A to B, but you don't actually feel anything. So I invite you next time you're in an airplane, or the first time you're on an airplane, close your eyes when it's smooth flying, block your ears, and you will find you won't be able to tell if you're moving. Now again, if the plane does have a bit of turbulence, accelerates up or down, or forwards and backwards, you'll be able to infer that. But otherwise, you have no idea how fast you're traveling. You have no idea. So that's an interesting property. That's an interesting property that you don't actually know how fast you're moving, right? Unless you have something to look at, something you can analyze your motion relative to. So as an example of some of the quirks of examining your motion relative to another object, let me show you another video. Let me switch to this video here. This one should have a watch, and we'll talk about it in just a moment.
Der Zug, der jetzt an Gleis 3 steht,
Alrighty, I'm hoping that caught you off guard a little bit, sorry. This person isn't moving to the right at all. In fact, it is the background which is moving to the left. So sometimes looking at relative motion can actually infer the wrong thing about your motion, or perhaps more so, it might not be the truth in a certain way. But those questions, as we'll find, aren't actually well defined. What is the true motion? Is this cart thing, I'm not sure what it is, the station, is it really moving to the left, or is the train in some sense moving to the right at all? Is the person in the train actually stationary with respect to the trees and stuff around it, or is there some other relative motion aspects to this where we could make a different claim? That's what we're going to be examining today. So I'm going to switch back to my slides. So here's what I like to do. I'd like to go through a bit of a thought experiment. You don't have to write this down. You don't have to write this down. There'll be some practice problems where you will get to write it down shortly, but I just want you to listen and absorb for the time being. So here we have a train, a car on a train, for whatever reason, and a person standing still. Okay, this could be you, could be whatever. In fact, it is you. So here's you, right there, standing still. If I asked you what is the velocity of the train relative to you, what would your answer be? Now, hopefully your answer would be 40 meters per second to the left. Right? That is the velocity of the train relative to you. That makes sense. Okay, what is the velocity of you relative to the train, or to the train driver? I want you to spend 20 seconds thinking about it. What is the velocity of you relative to the train driver? If you were the driver of the train, if your friend was the driver of the train and they saw you just standing still, what is your velocity relative to them as they drive past? Now, hopefully you would agree that the velocity of you relative to the train is 40 meters per second, but to the right. Yeah? To the right. Imagine you were in this train seat and there was some other person standing here. As you move past in your train, that person would whiz behind you. Yeah, so they're going in a sense the opposite direction to you. Okay, great. What is the velocity of the car relative to you? We're putting you back here now. What's the velocity of the car relative to you? Now here, I want you to think of, say, a travelator at the airport. You know, I'm not sure if you know what I'm talking about. They're like essentially like a treadmill. Right? They're a flat escalator. They help you to get somewhere quickly. Right? So the travelator is moving to the right, and you're walking on it. So you speed up. Right? Your velocities add. So you're traveling at the velocity of your walking speed plus the velocity of this travelator. So if you were thinking about this car and its velocity relative to you, I'm hoping you would agree that because the train is moving at 40 meters per second, that's carrying the car, and the car itself is traveling at 14 meters per second, that the velocities add. And so to you, the car is traveling at 54 meters per second to the left. All right, now I have a question. What is the velocity of you relative to the car? Now, what is the velocity of you relative to the car? And for similar reasons I mentioned earlier, you are moving 40 meters per second to the right relative to the train, but also additionally 14 milliseconds to the right relative to the car. Right? So to a person in the car here, they would see you moving in the opposite direction at 54 meters per second. 54 meters per second. Okay. Now I have a slightly different question. If we took you and we put you in there, into the driver's seat, we painted the windows black. Yep, painted the windows black, deprived you of any observation of what's outside the car. What is your velocity relative to the car? Relative to the car itself. What is your velocity relative to the car you are sitting in? It should be zero, right? It should be zero. The car isn't moving relative to you. You and them are moving at the same velocity. You and the car are moving at the same velocity. The car isn't moving faster than you, and you're not moving faster than the car. If that was the case, somehow you would be phasing through the fabric of the car. That doesn't happen. Okay? You are at the same speed of your vehicle, so your velocity relative to the car is zero. Zero. So when, for example, if you're traveling on the highway on the way to school or whatever, just down some road, even though you're traveling at 60 k's an hour or 100 k's an hour, relative to the car, you're traveling at 0 k's an hour. Now, you can't use that to try and get out of a speeding fine. If you said that to a police officer, you're going to jail. But the point is that, physically speaking, you are not moving relative to your car. Okay, and so we have these different perspectives now. We have this perspective. Sorry, we have the perspective of the person standing on the platform. We have the perspective of perhaps the driver of the vehicle, the driver of the train, maybe the train itself, the car itself. We have these different perspectives. Right? These are different reference frames, different ways you can observe the physics of this event. And so a really good question is, which one of this is correct? Is the car moving 54 meters per second to the left? Is it that are moving 54 meters per second to the right, to the car? But then again, to the train, you're moving 40 meters per second to the right. But then to the car, they're not moving at all. Which one of these is true? Which one is the true information that we can base our inferences off? Well, the answer is they are all true. Right? They are all correct, valid statements, just made from specific perspectives of nature. They are all true. And so here's where I want to define a frame of reference. It's a start slide, and I typically leave start slides for when you should definitely write something. So please write this into your books. A frame of reference is the viewing point or the perspective of an object or event. I'll give you 20 seconds to write that. A frame of reference is the viewing point or perspective of Okay. So take this example on the screen where we can see a rocket flying upward, and then we have this image on the right, and you can see the fuel inside the rocket as well. Whoops. So on the left-hand side, what you're seeing there is the flight of the rocket from the reference frame of somebody standing on the ground. You have somebody standing on the ground. They see the rocket leave the ground and move upward. What is the right picture, the right, video, I suppose? What reference frame is that? Where's the perspective? If you put a camera there, where would that camera be? Well, it wouldn't be on the ground, otherwise they would see what's on the left. Instead, this camera must be moving at the same speed as the rocket, or moving with the rocket, right? So this is the flight of the rocket from the reference frame of the rocket itself, or something flying next to it. Yeah. Now, if you actually look at this, if you look at that, the rocket doesn't look like it's moving at all. And this is what I was trying to get at when I started this lesson. Like, how do you know how fast you're moving? Yeah. If your reference frame is with the object and you don't have anything to look at relative to, you don't really know your velocity. Yeah. Okay. Now, there are many different types of viewing points. You could be jumping up and down and looking at something. That's a perspective. That's a frame of reference. You could be on what are they called? Like a Ferris wheel. That's a perspective. You're moving around and around and around. Could be just on Earth as it spins. That's a viewing point. You could be stationary in a laboratory looking at something else in a laboratory that's stationary relative to you. That's a perspective of things. There are many, many different frames of reference. Some of them are accelerating, some of them are still, some of them are moving at a constant velocity. There is a very, very special kind of frame of reference that we call an inertial frame of reference. An inertial frame of reference, please write this down, is one that is traveling at a constant velocity. An inertial frame of reference is one that is traveling at a constant velocity. This means that this frame of reference is not accelerating, meaning it's not speeding up or slowing down, but also it's not changing its direction, such as rotating, like circular motion. So inertial frame of reference is one where it is traveling at a constant velocity, not a constant speed, a constant velocity. Okay? All right. So let me explain to you why accelerating produces why that's not so special. Okay, when I say special, it's not because it's better. It's because it's a subset, right? It's an element of the many different frame of references that we have. Okay, so let me explain to you why spinning reference frames are a bit unusual. So on the left-hand side here, we have a camera, which is looking at a ball that's getting flung on this piece of string. So the camera is stationary, it's not spinning. The ball is spinning. And you'll notice that when the ball is released at this point here, it goes exactly where you expected. It goes this way. We'll just let it watch again. So it follows our predictions from Newton's laws and a known understanding of motion. It proceeds with that kind of behavior. But what I would like to do now is take the camera and allow it to spin with the ball. Okay, to spin with the ball. And I'll show that on the right in just a moment. So here we go. Here it's spinning. Let's chuck the ball and there it goes. And then we'll release it. I'll try and map out the direction. Okay, it does something like that. Right, it like curves off. We'll just let it play again. Now that is very unusual, right? Our known Newton's laws do not predict this kind of motion. And so that's why spinning reference frames or accelerating reference frames introduce these strange artifacts, this kind of arced or rotational motion. You can, in more sophisticated theories of physics, accommodate for this. They're called centrifugal forces. And but we're not there yet, right? They do not follow the elementary Newton's laws we have learned in year 11 and year 12, okay? And it's not the basis for explaining all the unknown problems I talked about at the very, very start of this lesson. So we're going to stick with inertial frames of reference because they demonstrate the kind of motion that we already know and we can use. All right. So here's a bit of a question for you. I want you to look at these 6 different options. I want you to think about which of these are inertial reference frames. Which of these are inertial reference frames? And I'll give you 30 seconds to think about which of these are inertial reference frames and which of these are not. Feel free to work together, of course. Okay, so let's go through some of these answers. So A, a skateboarder traveling at 8 meters per second. Technically speaking, that is an inertial reference frame. They are moving at a constant velocity. Now, if they're a bit bumpy, then technically they're not, but traveling at 8 meters per second, constant velocity, that is an inertial reference frame. A plane speeding up as it takes off. That is not an inertial reference frame. It doesn't have a constant velocity, it's accelerating. A person sitting in a Ferris wheel. Also not an inertial reference frame. They are spinning. They have a centripetal acceleration. So it's not an inertial reference frame. A car stopped at a traffic light. That is an inertial reference frame. Their velocity is constant, 0. A boat cruising at a constant velocity. That one's a bit tricky. Technically, that is true. But of course, boats are prone to waves and fluctuations and moving up and down. And so it's not a very good inertial reference frame. Okay, so theoretically, yes, a boat traveling at a constant velocity is an inertial reference frame, but practically, they are not. A person jumping up and down? No, they're accelerating up and accelerating down. Now, what's interesting is that Earth is also spinning. Right? It's spinning like a basketball, and then it's also spinning around the sun, and the sun is spinning around the galaxy, and so it makes an interesting question is, well, is Earth at all an inertial reference frame if it's spinning? Technically, no. But if we can conduct experiments on Earth because we are all spinning at the same rate. So it kind of cancels out that effect. But that non-inertial nature of the rotation of the Earth and the revolution of the Earth does impact astronomical observations because we're rotating relative to them. but that's not something we have to worry about, but just food for thought. Okay, what I'd like for you to do now is to write down this question into your book, and we'll go through the 3 questions at the bottom of the screen, but I'll give you a minute to just write that in. We'll do some actual calculations now. Okay. First of all, I actually want to change these to velocity. Should have thought of that ahead of time, but one take, one opportunity. Here we go. So, let's have a look. Relative to a stationary observer, an ambulance blares its sirens whose sound travels at 343 meters per second to the right. Okay. According to a stationary observer, the ambulance is driving at 28 meters per second to the left. A cyclist is going the other way, traveling at 17 meters per second to the right relative to the observer. What is the velocity of the ambulance relative to the cyclist? Okay. So what is the velocity of the ambulance relative to the cyclist? Okay, do we have that information anywhere? No, we don't. We don't have it all. We know the velocity of the cyclist relative to the person, but we also know the velocity of the person relative to the ambulance. So maybe we can connect these features together. We want to find the velocity of the ambulance relative to the cyclist. So I'm going to abbreviate that as VAC, the velocity of the ambulance relative to the cyclist. Okay, I'm hoping you agree that we can find this by finding the velocity of the ambulance relative to the observer plus the velocity of the observer relative to the cyclist, right? It's kind of like take just a step in between, a little intermediary step. So the velocity of the ambulance relative to the cyclist is the velocity of the ambulance relative to the observer plus the velocity of the observer relative to the cyclist. Yeah? We just take a little step in between by going through the observer, because that's all the only information that we have. Now you'll notice that the start and end letters are the same as what I'm looking for, and the middle two are identical. Okay, that's also a good way to sanity check whether you're on the right track. For those that do methods, it kind of reminds you of perhaps matrix multiplication, but nothing like that here. Okay, so what is the velocity of the ambulance relative to the observer? Well, are we told that? According to a stationary observer, the ambulance is traveling at 28 meters per second to the left. Let's go ahead and define left as positive and right as negative. So the velocity of the ambulance is 28 meters per second to the left relative to the observer. So this is positive 20, is that right? Yeah, positive 28. Plus the velocity of the observer relative to the cyclist. All right. So we are told in the last line here, the cyclist is going the other way, traveling at 17 meters per second to the right relative to the observer. So what we have here is the velocity of the cyclist relative to the observer. But what we want to find is the velocity of the observer relative to the cyclist. Now I want you to think back to that train, the train problem or example that I showed you. If you want to switch the perspectives of two observers, you simply switch the direction. So whilst it is true, yes, the cyclist to the observer is traveling 17 meters per second to the right, the observer to the cyclist is traveling 17 meters per second to the left. So that means positive 17. All right, and because oh no, I couldn't get, that's 48. All right, so it's 40, not 48, 45. Positive 45 meters per second. Meters per second. And it's a positive number, which means it is to the left. And that is exactly what we expect. Right, the ambulance is moving left, so we expect to the cyclist, the velocity of the ambulance, we expect that to the cyclist, the ambulance is moving really, really fast to the left. First of all, because it's going left, but also because its speed to the left will be a combination of both its own driving speed plus the velocity of the cycle, in a way. So, 45 meters per second to the left. What is the speed of sound relative to the cyclist? What is the speed of sound relative to the cyclist? Well, actually, it might be a good idea to try and pause this video and you spend 2 minutes trying to work that out. Try and work that out by yourself. I would invite you to pause here and then actually go through it. But due to the miracle of movie magic, I'm just going to go ahead and assume you've done that and go through it with you now. So the velocity of sound relative to the cyclist is the velocity of sound relative to the observer plus the velocity of the observer relative to the cyclist. Okay. The velocity of sound relative to the observer is given in this first line. Sound is traveling right at 343 meters per second. At right 343. So it's minus 343 plus the velocity of the observer relative to the cyclist. Well, that's positive 17. It's positive 17. So minus 343 plus 17, just a quick check on the calculator, equals to negative 326, which is equivalent to 326 meters per second to the right. Yeah. So the speed of sound to the cyclist is lower than 343 meters per second. And we should again kind of expect that. First of all, that it's going to the right because it's much faster than the cyclist. It'll keep going to the right. But also, because the cyclist, in a sense, is cycling away from the sound wave. So the sound wave has to do it feels like some catching up, so to speak. So it's not quite at its original speed. Question C, what is the speed of sound relative to the ambulance? So the speaker is actually, technically here, right? Gets emitted outward. And I can tell you right away that the speed of sound relative to the ambulance is 343. Meters per second. Perhaps I haven't actually asked this question very well, but when you're in the ambulance, you don't hear any differences in the frequency due to any changes of speed in the wave, because the wave is produced at your own location. You're not running away from it, right? It's being emitted at your location. Yeah? Cool. All right, so there's a little mathematical example. What I'd like to do now is really talk about the meat of special relativity, which is where all the conundrums come from. So I want to go back for a moment, and after this I'm going to let you go to do some textbook work. But imagine you had this circumstance. Imagine you were looking at this train that's traveling at 1,000 meters per second. Very, 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 very fast. And the car on the train, it's just sitting on the train, so it's moving along with it, but it switches on its headlights. Yeah? Now, to the person in the car, they would say that the speed of light is c, 3 times 10 to the power of 8. Yeah? What is the speed of light relative to you? Well, our expectation, whoops, I just erased all of that, awesome. The expectation is that the speed of light to us would be 1,000 plus c, right? Much like how when the car moves, you add the velocities. Similarly, when the light moves, you add the velocities as well. Now, this addition of velocities is often called a Galilean addition of velocities, named after Galileo Galilei. It's nothing you have to really, really know about, but it's just a kind of type of addition of velocities. So we expect that the velocity of light for us, standing there still watching this unfold, the speed of light for us is going to be 1,000 plus the original speed of light. What actually happens is that the speed of light is a whopping c. There's no addition whatsoever. So even if the train is moving the whole system to the left at an extra 1,000 meters per second, the speed of light that we see is just c. Here's what's extra funky. Let's say the train was moving at 0.99% the speed of light. Yeah, 99% the speed of light. And let's say the car was traveling at an additional 99% the speed of light. And then it switched on its headlights. Well, we would expect that the velocity of the light that we see would be c, the speed of light, plus the velocity of the train, 0.99 c, plus the velocity of the car, another 0.99 c. So it'll be, what is that? What's 0.99 times 2? All right, so it'll be 2.98 c. We expect the speed of light that we expect the speed of light that we would observe to be almost 3 times the typical value. The observation that we see is that the speed of light is just 3 times 10 to the 8. There's been no addition of velocities at all. Somehow, this kind of natural addition of velocities, this Galilean addition of velocities that we know and that do work for slower moving objects, don't work at all when it comes to the speed of light. We have tested this, and, well, not exactly with a car and a train, but we've tested this, and we've found that this is true. When you get close to the speed of light, and at the speed of light, this addition of velocities no longer holds. And that has significant implications for the nature of time and the nature of space. And we're going to be learning about that in the following lessons. But for today, I'm going to leave you here. Please write down any questions you have, and I'll give you some work to do now to flex your mind muscles. Thank you very much for listening, and have a good rest of your day.